I could not understand the relation between the omega curvature, that density thing, and the cosmological constant. I believe they are related.
Yes.
Could you elaborate on that?
Yeah, so there are two ways to say that there is a cosmological constant dominating the universe. One is through noting that the expansion rate of the universe is increasing with time, the acceleration. That was seen in the high redshift supernova, which got a Nobel Prize, right? But this was already, our community believes that we had already nailed it by finding out that the universe is geometrically flat and that the amount of clustering matter was not larger than 0.3. Already we knew these two facts. And the fact that the algebraic equation must add up to 1, we already knew 0.7 had to be matter which does not cluster. And it's very interesting that matter that does not cluster is also matter that accelerates the expansion. Okay? And that's a very interesting thing. Not coincidence quite, but it's interesting to note.
So, sir, I have a very naive question that what is there beyond the plasma screen, and where were they at the time of beginning or when Big Bang happened?
So the plasma screen is something that's shielding what we can see around us, right? Someone who is 43 billion light years away from us is seeing stuff that is happening beyond our plasma screen, but cannot see what is happening on the left side of us. So every observer is surrounded by that. So what is happening now is regular cosmological things. But the plasma screen, you notice, is in time. So it is because we can only measure things along that light cone, because the only way we know about the universe in the distance, at a distance, is through light. It comes on a light cone, and by the time you get to this plasma screen, the universe is hot, and it screens what is happening before that. So it's more a screen which is keeping you from knowing through electromagnetic electromagnetism observations, the universe prior to that time, 400,000 years old.
But what is the possibility? What should
So
be
that
there?
is what we are trying to find, because we see the plasma screen. Now it is like you see a plasma screen and you don't really know what is the, what kind of electronics is behind that. Right? It's the same thing. We are trying to see if the hints of that can come in the things that we are mapping. We cannot, go there, but we can obviously try to infer as much as possible from that. And there is a lot of information. It's hotter and colder, and also this linear polarization pattern tells you what kind of physics is operating behind.
Yes. Sir, if we use the gravitational waves background, so we'll possibly be able to see beyond the plasma screen, right?
Yes, we'll see well beyond the plasma screen.
So, sir, what will be the expected range of metric perturbations which we can expect from that?
Okay, so those are at the level. So these metric perturbations that you see in the plasma on the plasma screen at 10 to the minus 5 are metric perturbations that were created, and they have been frozen at that amplitude. So the metric perturbation levels are still at 10 to the minus 5 at that time.
So, sir, is there a possibility that it will lie within the LISA band?
No. Which one?
In the LISA band or any?
LISA band, no.
Yeah.
LISA band, yes, in terms of frequencies, but not LISA sensitivity. So there are things of getting more complicated 6 spacecraft configurations called Big Bang Observatory, which were proposed earlier, which claim to be getting down to a level where you would be able to see the same background in the microwave background as well as on scales of millions of kilometers.
So, sir, another question, how does the CMB Bharat mission fit into the INDIGO program? Like, what is the correlation?
In some sense, of course, INDIGO consortium, after proposing LIGO India, now LIGO India is a full-fledged project. The INDIGO consortium has become an advocacy group for all things gravitational waves. So I didn't have that slide, but there are 4 windows opening into the gravitational wave. So just like you have in electromagnetism, you have a radio window, you have an optical window, infrared window, ultraviolet, and so on. Similarly, we have a LIGO band, which is few kilometers, kind of, few hundred kilometers wavelength. and that is already opened up. LISA measures things where the frequency is about millihertz. This is about audio band, so 20 hertz to 2000 hertz. This is millihertz is LISA. Nanohertz, we can actually use pulsars as clocks and measure gravitational waves. That's also pretty mature. I mean, there was always this worry which window will break out. And at the largest scale, on cosmological scales, is the cosmic microwave background polarization that's measuring gravitational waves. So it just happens that LIGO broke the ground first and saw gravitational waves. And then these others will hopefully see in the next coming decade, these windows will open up.
But sir, pulsar timing arrays don't have that range of metric perturbations. Like they are not that sensitive in that.
No, they are
case.
quite sensitive. But the point is the gravitational waves, you see what LIGO is measuring is metric perturbations at 10 to the minus 18, right? 10 to the minus 21. I mean, actually, if you divide by the length of the detector, 10 to the 21, right? And CMB is measuring fluctuations at the level of 10 to the minus 5. So, in fact, the power spectrum of gravitational wave fluctuations in the universe is such that on larger scales, the amplitude is much larger. So, pulsars have a slightly lesser challenging scale.
Yeah. So in the CMB diagram, you showed the temperature and the polarization. There seems to be a correlation between the temperature fluctuation and the polarization. Is there any?
Yes, there is. So there is also another spectrum that we measure, which is the cross correlation between temperature and E mode of polarization. Okay, the B mode cannot correlate because temperature is invariant under temperature fluctuation is invariant under mirror parity. It's a scalar quantity, whereas E is also, but B is mirror anti-correlated. So T-B correlations are not possible unless there is parity violating physics, which can happen. And again, there are communities in high energy physics who have many interactions where you can imagine that there is parity violation, and we put limits on that. We have started, CMB has started putting limits, interesting limits on parity violation physics of parity violation processes in physics.
Yep. Sure.
So there was a cosmic drum model which you had shown in one of the slides. So there you had given a radius 150 megaparsec. What was that measuring?
That was telling you, so I told you, like, take the plasma and hypothetically, perturb it. So the cosmic drum, I didn't, spend time at, so to me, this is like how you know how well a tabla is tuned. So you're seeing the metric of the universe, it's like a membrane. And the way a tabalchi says it's well, he hits it with a hammer.
Yeah.
It's actually, he's doing the same thing. He's bringing out all the notes, doing green function. So we will do that, hypothetically. And if you do that, then there's a ripple, because the baryons and photons are tightly coupled. They are an elastic medium. So baryons like to get, wouldn't mind staying in the spike, but radiation has pressure and it pulls the baryons away. And anything that is elastic, if you tap it, there are waves going out. So this is a ripple that goes out. So analogy that I give to many in popular talks is, the picture is the following. You're standing by a placid lake, and suddenly there's a burst of shower, right? Raindrops fall. Everywhere a raindrop falls, there's of course perturbation there, and a ripple goes out. And then you take a picture after, say, 10 seconds, right? What you will see is choppy waters. But if you had the ability, like physicists do, you can take a Fourier transform of that picture, and actually you will see that in that 10 seconds, say a ripple, and all the ripples would have gone by the same amount, because, so you will have rings of a very specific size, say 1 meter. So the entire choppy water will be made up of droplets at a center and a ring of 1 meter. Okay, that's the decomposition. We are doing exactly the same decomposition, but on this plasma screen.
And one more thing. The gravitational wave background from the cosmic microwave time, why is detecting that a challenge considered to what has already
So that
windmill.
is, as I said, it's the level is much lower than you
Less
know,
than 10 to the power minus 21 also. Less than the current.
No, 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 no,
Listen,
no. It's not because that we are not measuring it. So we are trying to measure gravitational wave background at 10 to the minus 6, minus 7, right? But we haven't gotten there yet. Not because of the metric perturbations, but it's if you look at the temperature fluctuations associated with this worldly patterns, those fluctuations could be as low as tens of nanokelvin in a 3 Kelvin background. Whereas we have been able to resolve out fluctuations of a microkelvin. So we have to go a few orders of magnitude.
That's a matter of resolution in that background.
Matter of sensitivity of your detector.
We have two questions, one in the back and Shovik. And
You mentioned that one of the goals of CMB Bharat would be to map all of the dark matter. So that dark matter would be the foreground dark matter between us and CMB, that
Right.
is through lensing.
Right, exactly. So that would map out all the matter that is there from here to the, since you are a practicing cosmologist, so to a redshift of 1100, right? But that's, of course, up to a particular thing. And it gives you the integrated matter density around that. We have already started mapping maps at the level of what the Kobe maps were there for temperature in terms of the mass, integrated mass in different directions with Planck data itself. We will be making much more refined maps with CMB.
Thank you.
Shovik.
Just like you said,
Speak
that,
into the mic.
the cell phone detectors kind of pick up this picowatt signal, and the aim is to go towards attowatt capture. So in case of gravitational wave mapping, what is the current sensitivity of those detectors and what you are going to achieve?
No, so such detectors, as I said, with the cosmic microwave background, the technology exists.
Huh.
The platform doesn't exist. The
Yes.
technology exists, it's been put on ground-based detectors, telescopes in South Pole.
Uh-huh.
But the limitation of ground-based is that you can see only a fraction of the sky, right? So you can't see the whole sky. And also there are systematic effects because you have to make sure that you're not contaminated by signals from the ground and stuff like that.
Yeah,
But
so-
the technology of the detector exists that we want to
So,
do.
but in terms of kind of mapping the gravitational waves, what are the current sensitivity of the current detection mechanisms, and what are you going to
Yeah,
achieve?
no, so
in
I
the
just
future?
wanted to be clear that this has nothing to do with the LIGO
I'm
part.
fun.
LIGO uses laser interferometer fringes, movement of fringes, and there it's a standard photodiode which is very sensitive, which measures the amount of light that is leaked out as it goes out of the dark port.
I am possibly trying to understand how much of that gravitational wave in terms of its intensity, how much you can detect now and what you actually need to do to map these.
Yeah, so if you want, I mean,
About
we need to
the
get about
universe.
an order of magnitude more sensitive for the cosmic gravitational wave compared to what we have had in the previous space mission.
All right, so let's thank Tarun once again for the inaugural colloquium, and it's been a wonderful talk. And as a token of our appreciation, here's a small.
Oh, even as IISER faculty get it? Okay, great. Thank you very much.
Thank you very much.